All right, this is the video for section 10.3, geometric sequences and series. So our goals for this video are to find the common ratio of a geometric sequence, to write terms of a geometric sequence, to use the formula for the general term of a geometric sequence, and use the formula for the sum of the first n terms of a geometric sequence. So just the definition of a geometric sequence. So a geometric sequence is a sequence in which each term after the first is obtained by multiplying the preceding term by a fixed non-zero constant. The amount by which we multiply each time is called the common ratio of the sequence. And when we write these out, we use the letter R for that. Okay, so an arithmetic sequence is where we add or subtract the same thing each time. A geometric is a multiply pattern or divide pattern, but dividing is the same as multiplying by a fraction. And then R is our common ratio, what we're multiplying by. So on our picture here, we've got a graph of a sequence where the first term in the sequence is the number 2. That comes from this point here. And then the second term in the sequence is the number 4. That's the value of that second term. The third term is 8. The fourth term here is 16. And the fifth term here is 32. This is an example of a finite geometric sequence because there's no arrow on the end here to indicate that it keeps going. So it only has those 5 terms. The common ratio here then is going to be the value of 2 because that's what you're multiplying each time to go from 2 to 4 to 8 to 16 to 32. Now we call it a common ratio because it's what you get when you divide each term by the previous term. So 4 divided by 2 is 2. 8 divided by 4 is 2, and so on and so on. So that's why it's called a common ratio. All right, so when we write the formula for these, we can do it graphically. I have found that in a lot of my years of teaching, students aren't as good at knowing how to write the equation of a geometric sequence like this because they're just not as familiar with that as opposed to arithmetics, which are lines. And students have a lot of experience with lines. This one is a different kind of a function, and so we'll look at the pattern in a different way. So we're just going to say our first term in the sequence is, and I'm just going to use a sub 1, okay, it has some value to it. To get to the second term of a geometric sequence, we take the first term and we multiply it by r, whatever that common ratio is. So if I wanted to get to the third term of a geometric sequence, I would take the first term, I would multiply it by r, that would get me to the second term, and then I would multiply that by r again. Now I'm at the third term. To get the fourth term of a geometric sequence, I would take the first term, multiply it by r, that gets me the second term, multiply that by r again to get to the third term, multiply that by r again, and that gets me to the fourth term. So taking a look at this pattern then, and then trying to generalize this to an a sub n, so letting this pattern continue to get to an a sub n formula, we're going to take a look at these. So to get to the fourth term, I took the first term and multiplied it by r 3 times. Well, the shortened way we write multiplying by r 3 times is multiplying by r to the third. To get to the third term, I took the first term and multiplied by r twice, so times r squared. To get the second term, I took a sub 1 times r to the first. Technically, I multiplied by r once. And then to get the first term, technically I multiplied by r to the 0 power because I didn't multiply by r at all. So kind of following through then with this general pattern, the a sub n formula is always going to have the first term in it. Right, so that's a sub 1 times. Each of these holds that has an r in it, so that's going to be r. And then what I want to look for is a relationship between the term I'm trying to find and what that exponent is. So when I'm trying to find the second term, the exponent there is 1. When I'm trying to find the third term, the exponent there is 2. When When I try to find the fourth term, the exponent there is 3. So the relationship there is whatever term I'm finding, so 4, that exponent is 1 less. So in my general formula, my exponent there is going to be n minus 1. So that's the nth term, or the general term formula for any geometric sequence. Now, just like with linear, we can adjust if we need to. Say I don't have the first term, I can adjust the formula and say I want to use the third term instead, so a sub 3, and then I just adjust my formula accordingly. So if it's the first term, it's n minus 1. If I want to use the third term, I would adjust my exponent to just be n minus 3. It sort of matches with how we deal with transformations of sigmas. We can do that. So this is the most common, but remember that formula is flexible to be adjusted to however you need to do that. Right, another formula we need in this, and we're not going to go through where this one comes from, but it is a formula you need to know, and it's the formula to be adding up the first n terms of a geometric sequence, so the sum. And this is what the formula looks like. Okay, now the first term there is your a sub 1, and r is going to stand for the common ratio, and r can't equal 1. Doesn't really make sense really in a geometric sequence for r to be 1 anyway, because let's just say we started with the first term 3 and r was equal to 1. That means the second term would also be 3, and the third term would also be 3, and the fourth term would also be 3 because we're multiplying by 1 each time. Doesn't really make sense to use a formula then to find the sum of those. So I said, okay, find the sum of the first 4 of those terms. I don't need this formula to do that. I would just take 3 times 4, which is 12. Okay, so that's why they're including this note here. Okay, so let's do some example problems for geometrics. So our first question here is, find the common ratio of the given geometric sequences. And I think on your paper I corrected this typo here, but that's a decimal point. So how do we find the common ratio? Now this one isn't as obvious as the one I did earlier, but when you find that common ratio, you're trying to figure out what do you multiply by to get from this term to this term? What do you multiply by to get from this term to this term? So sometimes I'll write an equation like this. I know I have to take 256 times r to get negative 179.2. And so I'm going to divide both sides by 256. And that gives me an r value of negative 0.7. Now I'll just double check to make sure that that also works for the next one. So I'll take that negative 179.2. I'll multiply that by negative 0.7. And that should give me the next term, which is that 125.44. Okay, to be a common ratio, it should work for every set of terms. So for the next one, and that's an infinite geometric series because of the ... there at the end. For the next one, this is a finite geometric series, and I can go through that same process. So I use the first and the second term on this one, but you don't have to. You can go from the second term to the third term. So I could do something like this, 3 root 3 times r, that has to equal 3. So then I can divide both sides by 3 root 3 to get what the common ratio is. In this case, that's 1 over root 3. And that should hold then for, I did the second and third terms, but that should still hold for the first to the second term. So if I take 9 times that 1 over root 3, I should get 3. So let's check our work here. 9 times 1 over root 3 is 9 over root 3. And if I rationalize by multiplying top and bottom by root 3 over root 3, I get 9 root 3 over 3. And if I reduce that, I get 3 root 3, which is the term I would expect to get when I take that first term times r. Okay, so it doesn't matter which terms you use, but that's how you find the common ratio when it's not obvious, like the one I did earlier. This one right here, I could get that common ratio without doing any work because I know what I'm multiplying by 2 each time there. Oh, I do want you to notice, by the way, in this one, that I do have alternating signs of positive and negative and positive. And that's dealt with the common ratio by having the common ratio as negative, because when your first term is positive and you multiply by a negative, that means your second term is going to be negative. when you take a negative number and you multiply it by a negative number, that's what makes that third term positive. So that alternating sign issue is coming up again in a sequence. All right, in example 2, we're going to do some sigma notation here. So express the following in sigma notation. So we want the sum of the first 3 terms of the sequence, in which the fifth term is -6, and the common ratio is -1/3. Okay, now there's lots of different ways that students will sort of approach this question. So let's see what I'm going to do here. I'm going to do this as, they don't tell me what letter to use, so I'll use K, but you can like I or whatever you want here. I know I want the sum of the first 3 terms of the sequence, so I'm going to go from 1 to 3. That'll give me the first 3 terms. Now remember what follows here, so in the space following the sigma, is a formula that's going to represent the sequence. It's going to generate the first 3 terms of the sequence. Now they gave me the fifth term, and so I'm going to use my geometric, this is the explicit formula for the general term of a geometric sequence. I know this one's geometric because they give me a common ratio, and so that's a sub 1 times r to the n minus 1. But they gave me the fifth term, and I don't want to go back and find the first term, so I'm going to do -6, that's the fifth term, times the common ratio, which is -1/3. And then for my exponent, instead of doing n minus 1, I'm going to use k here, but I'm going to do k minus 5 because I'm using the fifth term instead of the first term, so I'm just adjusting that. And that's not the only way to do that. I see students doing that lots of different ways, but that's probably the quickest in terms of getting us a solution without doing a whole lot of excess work. All right, in the second one, I'm going to look at that first, and I'm going to decide what kind of equation that I'm dealing with. Is it arithmetic? Is it geometric? Is there some sort of other pattern? So I'm looking to go from 2 to -6. I could multiply by -3. To go from 6 to 18, I could also multiply by -3. To go from 18 to -54, I can multiply by -3. So this is something that's geometric. It's infinite because it goes on forever. The common ratio there being -3. So if I want to write that in sigma notation, and again, you can use any letter you want. I'll just use I because I know some people like to use I instead of K. I want to add them all up. So I'm going to go from 1 to infinity. And what goes in this space here is an explicit formula that represents that sequence. Now I know I've talked about those alternating signs a lot. Because my common ratio is negative, I don't need to do that -1 to the power trick. Right? This is one way you can deal with alternating signs, but I don't need to worry about for that question because when my common ratio is 3, when I write this formula, the signs will take care of themselves. So I'm going to use 2 here because that's the first term, times my common ratio, which is -3, and then I would have I minus 1 as my exponent. Now that having that -3 common ratio will take care of having those positive negative alternating signs. I do have students that sometimes will do it as, give myself a little more space here. They'll deal with the alternating signs using that -1 trick. So we want the first term to be positive, so I could do like I plus 1 here. And then they'll do the formula 2 times, but when they do their common ratio, they'll just do it as a 3. So this takes care of the alternating signs, so I don't need a negative on the 3 here that would also deal with the alternating signs. So that's a great answer here, but I've seen students do this, and that's correct too. What sometimes makes it challenging in this unit because you can get multiple answers, and they're both correct. All right, and then our last example is finding the sum of the first n terms of a geometric sequence. So we've got a geometric sequence here, 65, 13, 2.6, and so on. And we're not going to just type it in on the calculator, okay? It's easy enough to go to that sigma feature on your calculator, type it in, and then you're done. So that's what some students will do. They'll do a sigma, they'll write it in sigma notation, They'll type it on their calculator, they get an answer, great. And I'm happy if you can do that. I mean, you could clearly get the answer to these last two questions by doing that. Type that in on your calculator, type that in on your calculator, type that in on, well, these are infinite, so be careful typing those in on your calculator. But we don't want to do that in this question. We want to use that S sub n formula from earlier. So we're trying to find the sum of the first 6 terms. Now what that formula starts with up here is a sub 1, so in this case 65. And then it's 1 minus the common ratio raised to the n power. In this case, that'll be 6. I'm leaving space here. Well, let me just write r for now. And then my denominator is 1 minus r. Okay, so to answer that question, I have to find out what the common ratio is from this problem. So for this question, to find that common ratio, I know I'm going to have to take 65 times r to get 13. I know it's geometric because they told me that. Divide both sides by 65, and I get my common ratio here is 0.2. So then to find the sum of the first 6 terms here, I'm going to do 65 times 1 minus 0.2 to the 6th, all divided by 1 minus 0.2. And the answer there I get is about, so that's an exact answer. And now when you type that in your calculator, you're going to get about 81.245, I think, if we round that last digit. Okay, so it's a way of getting a sum of a geometric series without using a sigma feature. If we wanted to do this with a sigma, we could have done something like this. Find the sum from, let's use n this time, n equals 1 to 6, because I'm finding the first 6 terms. The formula here would be 65 times 0.2 to the n minus 1, because that's the explicit formula for a geometric sequence. Type that in on your calculator, you're going to get the same answer. All right, and that's the end of our notes for this section.